Welcome to one of two lessons on applied derivatives. In this lesson, we'll focus on rates of change. Let's begin here. We have this great NBA player from Latvia, of course, but even greater than him is this bicycle. Look at this beautiful bike. Guess what material that bike is made from? Well, that bike is made from wood. This is made by a company, a Latvian company called Materia Bikes, making these very, very expensive but very beautiful wooden bicycles. Really, really amazing. Okay, that leads us into a problem about bicycle production. So it says the total cost, C, for a bicycle manufacturer to produce X bicycles is given by this function. So we have this function and it represents the total cost of making these bikes. And it says X values are in the domain of 0 to 600. Okay, first question. Find the cost of producing the following number of bicycles, 250 and 251. So find that cost. And remember, X represents the number of bicycles, so use the function. All right, you've tried it, and you found out that it costs this much to produce 250 bicycles and this much to produce 251 bicycles. So you can see it's a high number, but that's the total cost, right? Okay, next question. Find the actual cost of manufacturing the 251st bicycle. So clearly there's a connection between what we just did and this question. So how can you find out how much it costs to produce that one extra bicycle to go from 250 to 251? What do you do with these two numbers? Okay, I hope the answer to that is clear. You take your cost of 251 and you minus the cost of 250. So you're just subtracting these two numbers. Because if this is the cost for 251 and this is the cost for 250, if you subtract them, you'll find out how much the cost went up for that extra bicycle, the 251st one. And that cost is this much. Okay, so now we know the cost for producing that 251st bicycle. Now do the same thing to find the cost of producing the 551st bicycle. So see if you can figure that out. It's not going to be the same cost, it's going to be different. So what is the cost for producing this one? Take the same approach we just did. Okay, to find that one, we need to take the cost of the 551st minus the cost of the 550th. So you've put both of those numbers into the function and subtract them, and you get this. Notice that when we get to this higher number of bicycles, the cost for that extra bicycle, the 551st bicycle, is less than it was when we were at 251. So as this company produces more bicycles, the cost per bicycle is going down. So the question there is why? Why do you think the cost is not constant? Okay, and some answers to that are there's the mathematical answer, and that is when you look at this function, this is not a line. Okay, the only way the cost would remain the same if we had a linear function, and everywhere you look on the line, you have the same slope, because that's what represents the cost, that extra cost per extra unit. It's a slope, but this is not linear. This is a parabola, and a parabola has a curve to it. So if you follow the curve, you notice it's curving downwards over time, and therefore the cost is going down over time. So that's the mathematical explanation. In terms of business, the explanation is something called economies of scale. As you maximize like your production and what, when you have a factory that's making something and a bunch of workers and machines, if some machines and workers sit idle, they're not being used, then you're losing money. But if you're using everything to full capacity, then your costs will go down because you're being as efficient as you can be with your business. So that's why costs go down as you increase production. All right, next question. It says differentiate C to find C primed. So find the derivative of this function. Let's do that first. Okay, here's the derivative. Check yours. And now find C primed of 250. So in other words, put 250 in here and also put 550 in here. Let's see what you get. All right, notice you get these two figures. There's something interesting here. What do you notice? There's something interesting you should notice. Okay, I hope you notice that these two prices are very similar to that cost of extra bicycle that we found here, very close. And we have those same numbers there, 250 in fact, right? So, and that is not a coincidence. Let's take a look at what's going on here. So we're going to talk about something called unit costs. Okay, again, when we have something that's linear, a unit cost is easy to find. So for example, here's total cost of some business and here's units produced. When we have a line, which can have a linear equation like this one, and we know this one has a constant slope and the slope is 5 here, we can see it in the equation, then we know that the cost for each additional unit is 5 more. So that slope, the constant linear slope, shows us the cost per unit, which is 5. Every time you add a unit, cost goes up by 5. Add a unit, cost up by 5. Add a unit, cost up by 5, and so on and so on. That's for linear things, but most things in the world don't follow linear patterns like that. In our situation, here's the graph of the bicycle function, and the function was this. It's quadratic. We can see it has that quadratic curve to it, but it was on a certain domain, so we don't even see the vertex. It just kind of ends there because the domain set only to 600. So we can see costs are going up. However, when we talk about here, we're talking about the slope here. When we talk about the slope of curves, we're talking about the slopes of tangents. So we take the derivative and we can get the slopes of the tangents, right? So for example, well, let me explain this first. Yeah, so you can see here the costs are first steeper. There's a steeper slope and then less slope and then even less slope. So the costs are decreasing as you're producing more bikes. And that's what we saw with the answers we found. The later bike cost less to produce than the early ones. The early ones cost more, higher slope. Costs are higher here, costs are going up less here. And that has a name. In business, that's called the marginal cost. And it is the cost of each additional unit. So we can find the marginal cost by using the derivative, plugging in the value of x, and then we say that's the cost of that extra unit. And then we go to another point, plug that into the derivative, that's the extra cost for that unit. And that's how that works. Okay, so there you can see the slopes getting smaller over time. Okay, let's try that problem. With all that same kind of thinking that we just had, read this problem, and let's see if you can figure these out here. Okay, for A, all we do is put 300 into the function, and we figure out it costs this much for 300. Okay, so the cost of 300 was just 300 into the cost function. We get this. Then it says the marginal cost, and that's what we were just talking about, the cost of each additional unit as you go. So that one is where you find the derivative of C. So it doesn't show it here, but if you found the derivative of that and put 300 into that, we would find out the marginal cost. Because this 1,120 represents the total cost, but this represents that extra cost per extra unit. So that's the marginal cost there. Okay, in C, it says find the marginal profit. So notice now it went from marginal cost to marginal profit. So do we have a profit model here? No, but we have a cost model and a revenue model. And you may remember, revenue is all the income that comes to a company, and profit is revenue minus costs. So you're going to have to do a revenue minus costs and find a new function, the profit function. So do that now. Find your profit function when you subtract those two. And then find the marginal profit. That means take the derivative of that profit one and find that marginal profit at 300 items. Okay, check your work. There's the profit function. And when you take the derivative of it and put 300 into it, you get that marginal profit. So what that tells you is at 300 units of production for this restaurant, they are making 11 euro extra. At 300, they make 11 euro for that extra item. So good profit for them. All right, hope that makes sense. Let's keep going. Okay, I'm going to demonstrate something else here. We're going to talk about the difference between average rate of change and instantaneous rate of change. Okay, this lesson is all about rate of change. So average rate of change is the slope of the secant line. So we're going back to kind of like what derivatives are. So remember, slope is just y2 minus y1 over x2 minus x1, which is rise over run. So let's say we want the average rate of change. We could begin here, and that point is, for example, is 50, 10,000. And again, this is our cost model for the bike production, okay? So there's that point, there's this point, 655,000. If we wanted to find the average cost, we can just connect those with a secant line and find the slope of that line. The slope of that line will tell us the average cost, because it's like saying we're taking curved data and we're making it into a line. So then it has a constant slope along that line, and that constant slope then represents the average. Okay, so here we could find the average. We could just do the y values subtracted, right? y2 minus y1, subtract that y value and that one, and then on the bottom you subtract the x values. That's your rise over run, it's a slope. That gives us 45,000 over 550, which gives us an average cost of 81.82. So that's the average cost of producing each bike if we go from here to here. But we know at different points of time, here is more expensive, for example, and here it's less expensive. So let's say we want to talk about the instantaneous rate of change. Instantaneous rate of change means what's happening at a moment in time. And in that case, we're talking about the derivative. So for example, see, it's the slope of the tangent line. We could say, hey, what's the marginal cost right there? And that's the instantaneous rate of change. So now we're talking about a tangent line. So we're not talking about average anymore. We're saying at that moment in time, how much does each extra byte cost? And for that one, we take the derivative. So there's our cost function derivative with 300 put into it, because that's 300 here. And when you solve that, you get 90. So the marginal cost at 300 units is 90. And notice that 90 is bigger than our average. And the reason is we're right in the middle here. The average takes into account the steep slopes over here and the less steep slopes here, so it ends up being less than this 90. This 90 is kind of in the middle, so you can tell it's bigger than the 81 average we found. Okay, please pause and consider everything here carefully, because this is the key of this part of this lesson, the difference between average and instantaneous rate of change. Okay, so try those ideas on this curve here, and let's assume that when we do the average from beginning to end, we are assuming that this point is at x equals 0 and this one's at x equals 9. Notice we don't know the y values there, but we can get them by putting x0 and x9 into our function, and then we can have the y values. So let's try it out. Okay, you've tried it. You're looking for the slope again. In this case, again, 9 goes into the function, 0 goes into the function. That gives us the y values, which we're subtracting, and then you subtract the x values here. And that average rate of this thing here is 1.1. So that's the average speed represented by this. Now find the instantaneous velocity at t equals 4. Okay, instantaneous at t equals 4 is a tangent line. We're looking for this speed or slope right there. It's called a velocity. Instantaneous velocity is found by finding the derivative of this one, which is called the position function. There's our derivative, put 4 into it, and we get an average speed of 1. Notice it's a little slower than this, and that makes sense. You can see, sorry, not average, this is instantaneous speed. So the average speed has a slightly steeper slope than this one at that moment in time. You can see that. All right, let's keep going. Take a look at this. Here we have another position graph. It shows the position of an object over time here. What would the derivative of this function represent? Okay, derivative represents slope, right? We know that. Or rate of change, right? We were just talking about rate of change at a moment in time, instantaneous rate of change. Okay, let's say then we're told that this function is the distance a diver is above the water based on the time after their jump. What does the derivative represent now? Well, the derivative represents rise over run, which is slope, right? But now we're talking about distance, change in distance over change in time, which is a rate or velocity. So again, we're talking about how much this distance changes in relation to x values, the time. So it's a rate of change, it's distance over time. Okay, let's try this problem in full. So here's the equation. We're trying to find the average velocity of the diver during the dive. And let's say they begin there and they end there. Although this one looks like they end right at 2 seconds, I'm going to tell you it's not exactly 2 seconds. So what you're going to do in this problem to begin, to find the average velocity of this diver, average is connecting those 2 points, you're going to need to figure out what the time is. And here's how we do it. We have our function and we set it equal to 0, because we want to know when this function is at the x-intercept, when y value is equal to 0. If you put that in your calculator using maybe the Poly simulation app, or using quadratic formula, you can solve this. So there's your answer. Okay, that tells you that this is 2.01, just past 2. Okay, so now we know our 2t values, so we can find the slope. That's the average. So find the slope there. We know we have a time of 0 and a time of 2.01. So put those into the function to find your y values and find the slope. So here's the slope. Put those into the function, find your y values, subtract the x values on the bottom, and you get this average speed of this diver. Now, change it up. Let's say you want to find at the moment in time there, that's in B. At the moment they hit the water, what's their slope there? What's their speed there? Okay, that's instantaneous velocity. You put into the derivative, you put your 2.01 x value, and you get that speed there. And you can see that speed is much higher than the average, because at that moment they're going much faster, much steeper slope. Again, pause and study everything carefully. Okay, now let's do some less graceful dives. This is me jumping into a pond. Fantastic. All right, try this one here. We have this function. We're going to find the average rate of change. Let's check our work. There's the function, average. We're going to use these 2 points. There's the average. We found that. Now B, we're looking for the derivative. This is a little tougher now. And then the instantaneous rate of change. Check your work carefully here. This was tough.